All right, guys, we're going to start section 6, which deals with growth and decay. So previously we analyzed problems involving exponential growth. Now we're going to solve problems involving exponential growth as well as exponential decay. So some of the terms we're going to come in contact with are the equation for exponential growth, compound interest, the equation for compound interest, and the equation for exponential decay. So let's get into exponential growth first. The equation for the number of blogs is in the form y equals a times 1 plus r to the t. Now that's the general equation for exponential growth, because when you add r to 1, it makes the number that's being raised to a power bigger than 1. And remember what we said, when the base here that's underneath the exponent is larger than 1, you have growth. When it's less than 1, you have decay. So in general, here's how the formula breaks down. Y is the final amount. A is the starting amount, or we call that the initial amount. R is the rate of change. Typically, they give that to you as a percent. You then have to put it in decimal form before you substitute it into the formula. Now, I'll just say this. If you have something, say, 8.1%, even though there's a decimal in the percentage, that is not decimal form because it's still in percent form. So you have to move the decimal 2 places to the left. So if they tell you the rate is 8.1%, then you would use 0.081 for your value of r. T is typically the time, and r is going to be positive here, okay? So let's try one out. The prize for a radio station contest begins with a $100 gift card. Once a day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. So write an equation to represent the amount of the gift card in dollars after T days with no winners. So in this case, the initial amount is $100, so that goes in for 100. The amount of increase per day is 2.5%, and remember, you got to move the decimal 2 places to the left, so that's why we put 0.025 in for r. And then you just simplify the addition inside the parentheses, and you get 100 times 1.025 to the t. Do not multiply the 100 times the 1.025, because the 1.025 is being raised to an exponent, so you have to do exponents before you do multiplication, according to the order of operations. Okay, so this is the simplified form of the equation. For part B, we want to know how much will the gift card be worth if no one wins after 10 days. So in this equation, T represents the number of days since the contest begins. So after 10 days, you substitute 10 into the equation. So if you're evaluating this on your calculator, you would do 1.05. Well, here, let's just you do 100, parenthesis 1.025 up to, up to the 10th. Okay, it's important to enter the parentheses. So you get 128. So that rounds to the nearest cent, because it's money, to $128.01. So after 10 days, the gift card will be worth $128.01. All right, here's one for you to try. Go ahead and read the problem, hit pause, and hit play when you're ready to check your answer. Okay, we're back. A college's tuition has risen. That's indicating, oops, I kind of crossed it out instead of underlining it. The word risen indicates that it's exponential growth because it goes up each year since 2000. If the tuition in 2000 was $10,850, write an equation for the amount of the tuition 2 years after 2000. So A is $10,850. R is 5%, but as a decimal, it's 0.05. So Y equals 10,850 times 1 plus 0.05 to the t. That simplifies to 10,850 times 1.05 to the t. Predict the cost of the tuition in this college for 2015. So the time of this recording, that would be 2 years ago. Well, you don't put 2015 in for T because the T represents the tuition T years after 2000. So you would do 10,850 times 1.05 to the what? Right, to the 15. Okay, so 10850 parenthesis 1.05, close the parentheses to the 15th, and you get $22,556.37. So you round to the nearest cent, which is the hundredths place, and that is the estimated cost of the tuition. Notice that in 15 years, the tuition has more than doubled, because if you add 5% each year, you're not just adding 5% of the 10,850. You add 5% for the first year, then you get a new amount that's a little bit more. Take 5% of that. The next year, you get a new amount that's a little bit more than that amount. Take 5% of that. Add that back in. So each year, you're adding in the amount that was added the previous year. Okay, so you don't have to understand all that. Just know how to use the formula. Okay? All right, so let's talk a little bit about compound interest. Compound interest is interest earned or paid on both the initial investment and previously earned interest. It's an application of exponential growth. What can happen, though, is that the ones we just did with the exponential growth equation was if it happens every year. Okay, every year. Well, what if there's more times that it's compounded than every year? You have to add the n factor. So it's the same exact equation pretty much, except you divide the r by n and you multiply the t by n. And what n represents is the number of times the interest is compounded per year. And what that means is that's when the interest is added in. So in the previous examples, it was just the interest was added in at the end of each year, and then that was the new starting amount. Well, sometimes accounts don't do that. Sometimes they add it in at the end of every month, or the end of every week, or the end of every day. They add the little bit of interest that was built up over that time period, and then on the next day or the next week or the next month, they start with that new balance. So let's see how it works. Maria's parents invested $14,000 at 6% per year, compounded monthly. Okay, so you got to think, how many times per year would it be compounded if they compound it monthly? Well, that would be 12. How much money will there be in the account after 10 years? So we use our formula. The initial amount is $14,000. The interest rate is 6%, but as a decimal, it's 0.06, so that goes in for R. The N is the number of times it's compounded per year. So that's what goes in for 12. For N here is 12, and 12 here as well. Because remember, monthly, there's 12 months in a year. And then how many years are they doing it for? 10. Okay, so if you simplify this and you get 14,000 times 1.005 to the 120. If you carry that out, you get $25,471.55. This 1.005 here came from dividing the 0.06 by 12 and then adding that to the 1. Okay? So here's one for you to try. Go ahead and pause the video. Okay, we're back. So determine the amount of an investment if $300 is invested at an interest rate of 3.5% monthly for 22 years. So the P is $300. That's the principal or the initial amount. The rate is 3.5% or 0.035. The number of times it's compounded is 12 because it's monthly, and the T is 22. So the account balance is equal to the principal, $300, times 1 plus the rate divided by the number of times, 0.035 divided by 12, to the number of times the number of years, power. So 12 times 22. So when you enter this into your calculator, you just have to be very careful. You could enter it all in at once, but make sure you have things in parentheses. So 300, I'll show you how to do that. times 1 plus 0.035 divided by 12. Now here's where you have to be careful. You have to put the 12 times 22 in parentheses, because if you don't put it in a calculator, the calculator will not know that you're multiplying the exponent of 12 and 22. It's just going to do the whole problem and then multiply that answer by 22. Okay? To get around that, you can multiply 12 by 22 first and then put that number in. Okay? So you would get $647.20. Okay? So let me show you another way to do this. You could do the 0.035 divided by 12, and that gives you that number plus 1. So you could think of this as 300, let me just divide that off there a little bit, times 1.00292, and then 12 times 22. This is 264. So if you divide and add this number together and then multiply to get the exponent first, then you could simplify the problem a little bit. And these are zeros. Okay. Now, when you divide here, this is oftentimes going to come out to a longer decimal. Go out as many places as you can when you add the 1, because that's just going to make your answer more accurate. So if I do 300 times 1.00292 raised to the 264th power, I should get a number that's pretty close. Now, the reason this is a little bit more than the original amount we got is because the r is the 1 plus r over n is 1.002916 repeating. And I rounded it up to 1.00292. See, I rounded it up a little bit. And that little bit of a difference, when you raise it to the 264th power, ends up making quite a significant difference in the answer. Okay? So that's the answer for that one. All right, that's it for this video. Please stay tuned for the next one, where we're going to talk about a little bit of exponential decay. See you there.